It's my pleasure to introduce Hugo Tavares, who is a colleague who used to be in this faculty, and he's still in Lisbon, but in some other place. And he's going to talk about free boundary problems and no long-range interaction. Thank you.
Okay, thank you. So now I will use my microphone, so maybe it's better to... Okay, it's turned off. Okay, so first let me apologize for being one that only comes for his seminar, but I have a small baby at home, so to manage, I'm using the advantages of the online, of being hybrid, okay? So the second thing is that this will be slightly off topic, so I don't work directly on the topic. So, but I decided to bring something which I think could interest everyone. Okay. So this will be a joint project. It's part of a long program which slowly is moving forward. Together with, at the beginning with Susanna Terracini from Torino, like me maybe, and then Alessandro Zilio from, is now at the Université de Paris, and Nicolas Soave, maybe some of you know him, and Nicolas Soave from Milano. Okay, so this based on these two, so one from 2018 and this one which was submitted before the summer. So let me summarize what I'm going to talk about. So it's going to be free boundary problems that interact from a certain distance. So there will be no fractional Laplacian. Okay, so the interaction will be different. Okay, you can think as you will see, if I have a particle here, it will interact with another particle maybe in a small neighborhood. And I will deal with a minimization problem, okay, that can be applied to either densities or shapes. And just to fix ideas, today I will work on shapes that have a long range interaction. So they don't overlap and they are actually at a certain distance. So let me start very slowly, since I'm a bit off topic, by trying to tell you what is in general a shape optimization problem. Okay, let me just move this below, otherwise I can. The things here, so problem. Like this, so think you have, so you will have a cost function, okay, whose domain is made of a class of sets, so class of subsets of Rn, okay, and now you want to minimize the cost among all shapes in this set, which can be a class of open sets. You can put convexity, you can, depending on the application you have in mind. So this is very general. So let me now take a particular example here on the right-hand side. So let me take one which is quite famous, which is the cost of something is the first Dirichlet eigenvalue of the set, okay, and now you want to minimize, okay, so the answer is a ball with, for instance, a fixed volume, okay, with omega being open, say, okay, so in this case, this is the set A, okay, the open set with a fixed measure, and the answer is the ball. You can take higher eigenvalues, the answer is harder, okay. And so this is an example. So I'm not going to do this. I'm going to do a kind of a subclass of this, which are, let me call it optimal partition. So it will not only have one set, but several sets, partition problems. Okay, and so the idea, imagine that you, I don't know, you have a structure made of several components and you want to optimize each one of the components of the structure. Okay, so you can take now the cost function, which will, let's say, take k sets and will assign it a certain cost. And now you want to minimize the cost of k sets, which do not overlap. So not overlapping means that each two will have disjoint intersection, okay? And we are in a certain class. Okay, so On the right-hand side, let me then speak about the particular case, which will be spectral. I will try to motivate it here below. Spectral optimal partitions, which is optimal partitions, which will be, if you want, okay, if you take as test function, for instance, the sum of, let's say, the first eigenvalues. So you have, for instance, okay, and let's take A as the subset of a certain fixed region, okay, open. So imagine that you have a bounded set. Now you take a partition. Okay. I'm not taking the union to be the whole omega, but then since you are minimizing, it will happen that thing, okay? But take a partition in this broader sense. You compute in each set its first, say, eigenvalue. And now you ask yourself, what is the, if there is a partition which minimizes it, and what are the properties? Yes?
Is it with respect to that machine?
Yeah, sorry, yeah. One is used to things, what else? So, okay, let me write it here. So this is associated with the Laplacian with Dirichlet boundary conditions. Thank you for the question. Okay, now this is just an example here on the right-hand side. Let me motivate a bit this example, which you can find in the literature. So it's one particular example. So it's a good, so these problems are tough, okay? If you want to start learning about this, there's a very nice book by Bukur and Butatsu, which I recommend. And you can think about this problem, this particular, as a good toy problem where you have good properties. So you have the eigenvalues are monotone with respect to set inclusion. So you have good monotonicity properties. And you can define this, you can find in this book, it will not be my approach. You can define a weak gamma convergence among sets, and you can prove that eigenvalues are a good example of something which is, for that convergence, lower semi-continuous. Then, okay, this is from more the mathematical point of view. People like Bernard Elfer and Hoffman Ostenhoff have connected this kind of problems with understanding of nodal sets of Dirichlet eigenvalues associated with the eigenfunctions of higher eigenvalues, okay? And then I will do a bit this connection today. They are also related with certain elliptic systems, okay, which also appear as when one looks for standing waves of Schrödinger systems, okay? So you have several ways of dealing with this. So what I will do today, so I will start by explaining that these kind of things are already known, okay? What I will do, if you remember the title, so let me maybe choose green, I will now put the long range interaction. So this is short range in the sense that the sets do not overlap, but they can be one side by side, okay? So the long range would be to include some restriction of this kind. So let's assume you have a kind of a wall between the things, so that the distance between two sets is at least a fixed r. Okay, now this slide is already a mess, so let me clean it up like this. So this will be my problem for today. So given a certain number k of sets and a certain distance r, I take the set of k partitions, okay, where I have the distance between two sets of being at least r. So this is an example of a partition, so this is a nowhere zone, okay? I cannot put material here, okay? And you will see that this makes the problem much harder. And now this is my minimization problem. So I want to minimize just to fix ideas, okay? If I have time at the end, I will give, okay, I can take an f of this kind, but this has the good properties, so let's keep it simple, okay? Like the first of the first Dirichlet eigenvalues for the Laplacian among these partitions. Okay, So before going into the results and a bit more of a literature review, let me explain that there is a very natural weak formulation of the problem. Using, instead of sets, let's use functions that you can think of as densities of something, okay? For instance, particles, if you want particles. So if you take, suppose that you take a partition, okay? And now in each one you have a first eigenvalue, take the eigenfunctions, okay? Then they will be a test function of this, okay? So you have the sum of the Dirichlet energy, L2 normalized, and now the condition of the sets being at distance at least R translates into the distance between the supports of the densities being at least R, okay? So this is smaller than or equal to our problem. We want to use this to show things about our original problem. We can do it when we know, for instance, if I take something here, and now the natural candidate to go from here to sets again is the positivity set, okay? If I know that this is open, so for instance, if the UIs are continuous, so I already need to prove a regularity result, then I have equality, okay? So now with this, I can tell you what is the program for the talk, okay? So I will show you that this has a solution and the equivalence between the weak, so using densities, and the strong using sets formulations. Then I will speak a little bit about its relation with the elliptic systems, okay? Where you can think about something which is competing in a non-local way. Okay? Imagine I have a particle here and it influentiates. It's competing with something which is in a neighborhood of radius R. Then I will do some regularity theory. Okay, so what is the free boundary here, by the way? So it will be these boundaries here of the sets. So if you have a minimizer, you want then to study what is the regularity of these sets of the partition. And also what is the optimal regularity of the eigenfunctions. Okay. Not knowing nothing a priori, okay? Just you have a minimizer of something, you are in H1, and now you want to prove that everything actually it will be Lipschitz and the boundaries will be maybe regular. And then to study the long range with the short range problem, doing the asymptotics as R going to 0. So this is the recent part of the work, okay? And finally, to deduce a free boundary condition. So I will explain exactly what this is when I state rigorously the results, okay? So, so now I will first do a very quick 2 slides literature review about what is known of the short range that I started introducing, where the sets can be side by side, where more or less everything is known. And this will help me to explain the differences with respect to what we got recently for the long range, okay? Then depending on the time and of your faces, I will maybe give some ideas about the proofs and then other examples and open problems. Okay, so just a crash course on what is known in the short range. Okay, like this, without spaces in between. So let's recall, okay, R is 0, the distance. So you just ask the sets to be mutually disjoint. Okay, so this is an example of a partition, just to recall. And this is the weak formulation. Okay, so I replace this by either the Rayleigh quotient or this and putting the normalization here. And I replace this information between sets by this local information between 2 different densities. Okay, at the same point, they cannot, the 2 densities cannot coexist. So either one of them is necessarily 0. Okay, so these are what I'm going to state is a collection of many works. As I said, you can take the point of view more of maybe calculus of variations and working only with this formulation by Bucur and Butazzo and that school. And then you have the connection with elliptic systems, which is more from here on, which actually helped improving the regularity. So what is known? I told you that everything is known. So what is everything? So so the set has a solution. Okay, this has a solution. Okay, first thing. Now, if you now take the eigenfunctions associated with the optimal partition, they are Lipschitz continuous, and this is optimal because of op lemma. Okay, so you have an equation here in the set. You have an eigenfunction. Okay, here you have 0. So the gradient is necessarily discontinuous. Okay. Of course, that could be something between Lipschitz and C1, but okay, it's Lipschitz. And then how about the free boundary, which in this picture will be these lines that I draw here. So to tell this in a short way, you say that this is n-1 rectifiable. What does this mean? So it means that the Hausdorff measure is at most n-1. And now gamma, which you can characterize as the common nodal set of all the eigenfunctions, is split in 2 regions, as you can see in this picture. Okay, you have the regular parts, which are these curves, and then this singular, let's call it singular parts. So in general, you can also prove that this is the picture, even in higher dimensions. You have a regular part, which is a union of regular hypersurfaces. Let's skip this for the moment. And what's left is small, in the sense that the Hausdorff dimension is n-2. And you can also stratify it again. So you can also say that this set is something of union of n-2 manifolds with something of dimension n-3. Let's just look at the picture if you want. In 2 dimensions, this is the picture. Then something that I will need to explain a difference between long and short range is, okay, the sets do not overlap. Let's take the corresponding eigenfunctions. Okay, they meet here. They are both 0. What happens to the derivatives? The minimality implies a kind of a reflection law. Okay, so if you want the 1D picture, okay, if you put yourself here and you look in this direction, you will see that the way they arrive at the boundary is the same. So they vanish, and there is a reflection law. Okay, and this is different from Z. Okay. In the long range, this will be much more complicated. Okay, what would happen? The curvature will play a role. Okay, so this is basically what is known, and just a relation with competitive interactions is that one way of proving all these results is to connect this with, so the problem is that they do not overlap. So let's allow things to overlap. So you can replace this constraint with something that is competing. So maybe you can use this idea to do some other things. So let's allow things to overlap. So just work here. And now let's minimize the energy. Let's put this penalization term in the energy. Now, if beta is very, very large, the facts, so this needs to be small if I want to minimize things. So at the limit, it's natural that they tend to overlap, okay? And the advantage is that, okay, you have a system, very simple system. You can see this as a singular perturbation of uncoupled equations of the eigenfunctions, okay? And this kind of, you can use this is variational, and you can use this to prove the regularity of the limit. Okay, so this is the connection. This you can also think, just to use the word Schrödinger, you also arrive to this when you look for standing waves of associated with Schrödinger or Gross-Pitaevsky equations, okay? This is another motivation. Okay, just to explain why the long range is difficult, let's, in one slide, what are the kind of arguments that one uses, which are typical when one studies free boundaries. You have blow-up arguments, which is the following. So if you want, for instance, you want to study the regularity of this boundary between omega-1 and omega-2, what you do is you do a zoom at this point. What is the zoom is you take this rescaling, okay? This will be a parameter which will go to 0. You have to normalize it conveniently so that you find something at the limit, and you use these kind of things to study this. So why is it difficult to use this kind of argument when you have something that interacts at a certain distance is that if you zoom in here, you lose all the information that you have far away. Then you have Liouville type results and something which is called monotonicity formulas. And I will just state this one to give you an example if you don't know them. But they are basically very clever formulas that help you with very few regularity assumptions to study the behavior of certain functions close to some point. So you typically take some integrals on balls centered in R0, and you study how those quantities evolve when the radius increases or decreases. Okay, this is where so let me just give you an example, which is one of the famous ones, the Alt-Caffarelli-Friedman formula. So it's very easy to state. So suppose that you have two harmonic functions, not everywhere, but here. So just split the plane in two regions. And now you take one harmonic functions in one region, another harmonic function in the other region. They are continuous everywhere. So this is the positivity set of U. And so here U will be 0 and the other way around. So this is the positivity set of V, and here V will be 0. So they meet at this common boundary, say, which is the free boundary. And now you ask yourself, okay, can this U and V be completely arbitrary? And the answer is no. So if you take this product, so you may think about this as an average. It's not exactly an average because you have the fundamental solution, but think about it as an average. So this is telling me that I center myself here at one point, and the product of the averages of U and V, of the gradient of U and gradient of V square, is bounded. This is one of the, so in particular, when R goes to 0, this does not blow up. This helps, you can see immediately that, okay, this is not completely arbitrary. You know, for instance, that if one gradient blows up, then the other needs to go to 0. So you can already see how this can help improving Lipschitz estimates, for instance, okay? So the fact that you have here the fundamental solution is just technically for the proof. Just think about it as the product of the averages, okay? Okay, so this was a bit a short overview of, okay, at what time did I start? Just to control my time. 45, okay. So let's see what's fun in when one passes to the long range. Okay, let's recall it. What is the problem now? So CR was the original minimization problem. So you had the sum of lambda ones. Now with this distance constraint, okay, so this distance needs to be at least R. Of course, being a minimizer, it will be R. And in the weak formulation with densities, with functions, okay, you have the sum of the Dirichlet energies, L2 normalized, and now this between the supports. Okay, let's see the result. Okay, the first one is not surprising, right? We could get away with obtaining a solution. Okay, so starting from the weak formulation, you have a minimizer. Then how is the system? How do you perturb? How do you do a singular perturbation? In this case, you have to do a non-local thing. You have to use a convolution. So before, you had here a Dirac delta. So you had here an interaction at the same point. Now you want that the presence of someone here competes with something in a ball of radius R. So you can use, for instance, the characteristic function of the ball or some potential like this. So you have a non-local interaction between the densities and you're penalizing this. So when beta goes to plus infinity, you have something which is at a certain distance. Okay. What distance? R. Okay, this was just an information. Now, optimal regularity. So this is a Lipschitz continuous function. I will speak a little bit why. Globally, you have a subsolution and you have, as you wanted, eigenfunction. In the open set, now this is an open set because you already know actually that DOIs are Lipschitz continuous. Okay, so as in particular with the weak formulation of the problem, you have a solution of the original problem. Now, we could not get yet, this would be the major goal, the regularity of the boundary, okay? From what I tried to explain, when you zoom in, you lose all the information, so it's a harder problem. So what could we get? The fact that we are minimizing something at a certain distance makes immediately, it's not hard to prove that the set, the positivity set of have an exterior sphere condition. So you can always put a tangent ball of radius r from the outside, okay? And this ball is always centered at the boundary of another set, okay? This is the first thing. So this is an implication. So if you want me to repeat something, please let me know. So you have, for the optimal partition, each set satisfies an exterior sphere condition of radius r, and this ball is centered at another one, okay? And we cannot get the regularity, but actually we know at least that the perimeter is finite, okay? This is actually a consequence of a very nice result, very general result by Caffarelli, Patrizio, Kitalo, which tells you, using viscosity solutions, that if you have a closed bounded set, and now you take the set which is at distance k from this set, the perimeter is finite, okay? Okay, and now, so I'm telling that we could not get the regularity, so let's see at least, okay, this is because of that. Let's see at least what replaces what in the local case was the reflection law. Let me recall it here. So in the short range, let's say short range, I had that the normal derivative would match the normal derivative on the other side. Sorry, this is because of a bit of sweat. Okay, so what replaces now this thing? So we have to assume regularity because we cannot prove it yet. So if we have regularity, let's assume that we take a point x naught, and that we have that the hypersurface the boundary is already a hypersurface. Okay, let's make this technical assumption, and I will explain you why in 2 slides. So since you have an exterior sphere condition of radius r, you immediately have that the principal curvatures are at least 1 over r. So let's not allow them to be 1 over r. Okay. This is technical. But then on the other side, you will also have a regular surface, hypersurface. And now this is, before this was 1. Now the curvature plays a role, okay? So the way they interact, you don't have anymore a reflection law, but you will have a product of the quotient of the curvatures. Since the curvature on one side is actually a function of the curvature on the other side, because this point is just this point plus the exterior normal here. Actually, if you prefer, you can see this thing as a function of r. It's 1 minus r ki of x naught. So you can see the dependence on r, and when r goes to 0, this matches so that they match one another. Okay, I will show you. This is very easy to give the idea of how to prove these kind of things, especially why should the curvatures play a role? It's not hard to explain. So why do I ask that technical assumption of being the curvatures smaller than this? Because otherwise you have to exclude this kind of things, okay? You can have, so take this set, which here is regular. So a part of a sphere, okay? Now this set clearly has the exterior sphere condition, okay? And if I take the set at distance, the radius, I have a cusp. So I have to exclude, this is part of the difficulty in proving the irregularity when you have this distance. I can perfectly have regular parts and on the other side, cusps, which are not regular, okay? So, okay. Now, finally, the more recent result, the behavior when r goes to 0. It's not as easy as one could think, but as expected, we can relate what was known to what we now have. So when R goes to 0, we approach the situation where the sets can be side by side. And so the optimal regularity for each R is Lipschitz. So we can prove uniform Lipschitz bound, so independent on the radius when R goes to 0. And using this, we can prove that minimizers go to minimizers. Okay, so we have an estimate, a precise estimate of the level sets. Okay, and in particular, we have this, which means that if I take a solution of the long-range problem, it will converge strongly to a solution. So this kind of connects the two problems, and then maybe we can use this information, since we know everything of the limiting set, maybe we can use this information at least to study the approximating solution, since we find it hard. Okay, so the results are over. Let me see. Yeah, so 45 you said, 50, 30, 38. Okay, so let me make a choice. Let me just explain the free boundary condition. Okay, and then so let's recall so that this is actually one of my favorite parts. So I will explain it here. Why the curvature, right? Where do they come from? So let me explain once again the problem. So we have a solution of this problem. So okay, this is omega. Let me just make here two sets. So I have here, yeah, the connection is not being, okay. We have here one set, which is the omega 1, and here you have omega 2, which is the positivity set of U2. And I have a point here, x naught. I have here a point, y naught. This distance is r. And I want to prove that the way the first eigenfunction arrives at this boundary is connected to the way the other eigenfunction arrives at this point through this law, okay, where this comes from. So what I will do, since I have a minimization problem, and everything is variational, I will produce a variation, an admissible variation that preserves the distance. Okay, this is where we use strongly the fact that we already know that everything is, the boundaries are regular, in such a way that we get this. Okay, so the idea is to do an admissible variation, plus using the minimality. Okay. So it can be, yes.
I have a question because
sure.
In your result,
yes.
We don't see the distance.
No, it's hidden here. It's hidden here. So this is, yeah, it's something that I told you, but maybe too quickly. So in the end, so this point y naught is, so if everything is regular, this is just x naught plus the exterior normal here. And the exterior normal here is minus the exterior normal at this point. So everything is related. So so one curvature is a function of the other. And if you write things down, you have this, for instance, and here you see the R. Okay, thank you for the question. Yeah. Of course, otherwise, what would happen, you're right? Yes, so maybe, yeah. So this is the thing. Okay. Right, so, okay, this is quite explicit, actually. So let me do it slowly. It's not. So let me start from omega 1, which is the positivity set of one eigenfunction of the set on this side. Okay, I fix a point here, x naught. And okay, so I will do a small variation. Let me take here a very tiny, a small ball. Okay, let me remember here the notation. So I take one ball, and now I take any test function. So test function, which is infinity of compact support here. Okay, so now the idea is that I will, which color should I choose? Okay, I will do a small perturbation like this to the outside. Okay, and consider this larger set. Okay, I will tell you what I will do on the other side. This will be quite explicit. Okay, let me try to write here. Let's see if it's better. F1 epsilon. It will be something from Rn to Rn. It will be a deformation. My hands are a bit sweaty, and this is why this is happening. So it will leave everything invariant in the complementary of the ball. Okay, and let me tell you what it does on this part of the boundary, which I will call gamma R1. So we'll just push outside using the normal. So I'll put here an epsilon. I will use the outer normal. I already have regularity, and put here the test function. Okay, something very natural. Okay, on the other side, I have to push inwards to keep the distance. Okay, so this was the original set. So now basically what I do is I use now this new normal of this set to push inwards. So I will just do something like this and consider this set. This will preserve the distance. Okay, let me just write a little bit explicitly. Okay, so on a point here, y, every y here is the image of a point on the other side. So I will just do the deformation as before, and I'll push it using the new normal of this new curve, this new normal, this curve. Okay, this not hard to believe that creates an admissible variation. And now I will use the minimality. So now I take the new eigenfunctions of these new sets, okay, and use something which is now known, which is called the Hadamard's variational formula. It tells you exactly how the derivative goes, okay? And not surprisingly, it only depends on the normal, so on the variation on the normal directions, okay? So basically, what is the derivative? So if you do the derivative in epsilon, you get this here, okay? And this will be the part that will count. So the variation will be explicit. It will be this on the one side, where let me just, the important notation is here the gamma 1R, which is this one here. It will be minus because remember, I'm pushing outwards. So the set becomes larger. So the eigenvalue goes down. On the other side, what is gamma 2 of R is just the image using the normal of this piece, gamma 2R. And it's the same thing, okay? For any test function. Now I use the minimality, so I have an inequality. If I let, so this was for all test functions. So if I make something approximating the characteristic function, I get this inequality. I was pushing outwards and the other one inwards, so I do the other thing. So I have actually an equality. And now the curvature, where do they come from? So if I now normalize everything, okay, since I'm assuming regularity, the left-hand side will go to this quotient at the center, okay? And now this is where the curvatures come from, because one part is this plus the normal. Okay, so when you do changes of variables, you'll see the principal curvatures coming out. And this is where this part is coming. So 15, I've spoken for 15, 30, 40. I have 5 minutes, right? I have 5 more minutes. Okay. Okay, the Lipschitz continuity, I will not tell you much. Okay, just to say that for fixed R, this is more standard because you can use something called barrier arguments. The problem is all these arguments break down when R goes to 0. So we had to, this is a whole paper now, the fact that how do we prove that you have uniform Lipschitz things when R goes to 0. Again, it's a deformation argument. Okay, and the problem is always how to produce admissible variations. Now that will also change with respect to R. Okay, but it's done by contradiction, assuming that a certain gradient will go to infinity, zooming in, but keeping very well a good track of that, because if we zoom in too quickly, we lose all the information on the other side. Okay, I will not go much. I'm sure that you didn't understand much. Okay, but basically my message here is the hard part here is when you do blow up, you might lose all the information on the other side. Okay, so we do this with new results, and it is and we can do an admissible variation. Okay, I will just finish by giving an example. So what do we use about the fact that we have a sum? So basically what you need is the cost function to be increasing and coercive in these terms. Okay, this is basically what we only need. So you can do the proof just using this information about the cost function. Okay, so not necessarily a sum. And you can also do other things, okay, without being eigenvalues. So since the proof for particular cases is already quite complicated, then we just say, okay, this can also be applied in other situations. So instead of eigenvalues, you can simply have harmonic functions, for instance, okay? And let me fix here. So you can have a typical minimization problem of the Dirichlet energies with boundary conditions, okay? And these kind of things also work. So you can actually write more general statements, okay? This is more the message of this slide, and the results are the same. So again, this is quite flexible. I was more focusing on the techniques. And the open problems, I think now you can guess some of them. So this would be this was our initial goal already 4 years ago, okay? It still is, we are progressing, but very slowly. Then the convergence, not only of the eigenvalues, but in a certain way of the free boundaries, okay? But we need to know the regularity first. And this should be a very hard problem, probably, which is the inverse. So so what we did was in one direction, which starting from the problem with an R, we let R goes to 0, go to 0. R goes to 0. Now the other way is starting from a limiting configuration. So actually, starting from a configuration where everything is side by side, can we build, using the fact that we know everything about this problem, can we build solutions with small r? Okay, thank you very much for your attention. These are some related works, okay? So we were very much inspired by this, which was not minimizing anything, but was considering elliptic systems, okay? Maybe not variational. And there is also a colleague here from Lisbon that has worked in this kind of things. So thank you very much for your attention.
Okay, thank you. Who is there a question?
I have a question. So, what are dynamic formulations of this problem?
Dynamic. What you can think about the yeah. So okay, you can always. So you have 2 points. So you can take the parabolic problem, for instance. Okay, and even in the local. So in the sense that you don't have this convolution, but everything happens at the same point. Things are hard, so how these free boundaries evolved. So, but people have done this kind of things. Or you can study this problem as coming from the Schrödinger equations in the sense that these are standing waves. Okay, but these are much, much harder. So this is already hard. So evolution problems, you can take these 2 points of view. Okay. When you take the parabolic one, maybe you want to make P equal to 1. So this is a kind of a Lotka-Volterra interaction, you see. And while in the variational, the motivation is coming from Schrödinger, but it's much harder. The parabolic is, we know already some things. In the Schrödinger, no, in the thank you.
We Yeah, well, you have a lot of questions.
It's nice. It's nice.
Well, precisely, so you get the example verification of the number of sets.
Yes, yes, yes.
So this is for R equals 0.
Yes.
And, for a positive R, are there any similar applications in quantum theory, or what does it mean to have this positive R?
No, no, I don't know about any. No. What I imagine this is that this is why I like the connection with the elliptic systems. You can think about something that, so the presence of maybe a particle here would interact with others with maybe with a V with a potential of this kind, right? So you can think about this, but the motivation was purely mathematical. It was actually, okay, not exactly. I mean, you have these kind of things by, I don't know if I have them on my computer. This is actually suggested by Gerard. Yeah, I don't have it here, but I would have to look. Wait, what is the name of the mathematician? Now I don't remember, but this kind of local, non-local things appear. And this is related to with this kind of thing. Not with systems. I've seen this for a single equation where you replace the cubic term with something of this kind. And I will look it up and tell you in 2 minutes, maybe, if I have it on my computer. Thank you.
Thank you. I have a question on the reference in the last page.
Yes.
So your problem is related to Tavares work, right?
Yes. So yeah, basically we are a bit complementary. So our problem is related when I take p equal to 2. Okay. But since he did something that worked with for all p, so something not using the rate, so it proves much less. So
my question is statements on the step regression model. So, and I know some there are some figures for aggregation model, and they also have the short range, long range. So, that do you have some, raw model? Do you have some up for aggregation?
For aggregation? No. So this would be taking the, maybe the opposite sign in beta, and probably they will concentrate at the same, but no, this is.
Any other question? Yes.
Just quickly, the functions you consider, if I got right, you consider any LP combination of the.
For instance, they also work. Yeah, something.
In the lower case, is ellipticity. I think that's not typically covered by your assumptions.
No. Yeah, I perfectly imagine. I understand your question. Yeah. So that could be. So one would need to prove it. Okay, and the typical thing is to do this, and then to send p to infinity. But one would have to prove this. But we are still doing. Yeah. And this would go to the maximum, at least heuristically, of the lambda. Exactly. Yeah, you could use this, but it's not something that we cover. No. Yeah, could be. I mean, we have a lot of open questions, so this could be also in the list. But the dream would be more to do the fixed case, the complete characterization of, because I mean, when you do this limit, you already need a good understanding of this problem, but we don't have it. So for the others, putting here a p does not change anything. Okay, that's the same thing. So yeah, Thank you.
There is a question in the internet from the audience here? No? And here? Okay, so if not, it's going to go for coming here and give us a
Thank you. Okay, I found the paper, it's this one. Then